Hello, and welcome to section 7.2, more circle stuff, radius and chord relationships. Okay, we need to start with some basic vocabulary here today, something we didn't talk about yesterday. And what it is when we talk about the the distance from the center of a circle to a chord. So here's the center of a circle, and I want to know how far that center is from this chord RW. Well, that distance, if we want to measure it, it's the measure of the perpendicular segment from the center to the chord. So to draw that in, I'm just going to line up my tick marks on my ruler. So I'm perpendicular to that chord, and we're going to draw it so that it hits the center. The length of that segment right there, this is the distance between the center and a chord. All right, now we have a couple of theorems that use this information, and here's the first one. It says if the radius or part of a radius is perpendicular to a chord, then it bisects that chord. So if AD, this segment, or if I just said segment AE, because that's part of a radius, is perpendicular to the chord, here's this chord BC, then the chord is bisected. So then this chord CB gets cut in half, which means this piece, CE, is congruent to segment EB. The chord is the thing that's getting cut in half, so the pieces of the chord are the congruent pieces. If we look at this next one, if a radius or part of a radius, again, bisects a chord, then it's perpendicular to the chord. So this one kind of flips it around. This one up here says if we have perpendicular to a chord, then the chord gets bisected. This one says if you've got a chord that's been bisected, well then that piece, that segment, must have been perpendicular to the chord. So segment AE is perpendicular to that chord CB. And this third one down here on the bottom, there's no picture here because it really kind of encompasses both of these two guys together. Both of these guys started with that center and drawing the radius off of the center. We started with a perpendicular, ended up with congruent. Started at the center and a perpendicular, ended up with congruent. This one started at the center, started with congruent, ended up with perpendicular. This one down here it just says that if you have both the perpendicular and the bisector part, well then of course that segment, it must have hit the center. So if you can think of these three pieces kind of going together, hitting the center, perpendicular to a chord, bisecting the chord. Those three pieces all go together. If you have any two of them, then the third one has to be true as well. Let's go ahead and take a look at a couple of examples here. Well, more than just a couple, several. All right, given circle O, where O is the center of the circle, AO is 5, DB is 2, and we want to find all of these pieces. Well, again, as always, the first thing that you're going to do is to label this diagram. So segment AO is 5. That's the radius. The radius is 5. Segment DB is 2. That's here. All right, now we have to find all of these things. Let's see. First one says OC. Now, OC is this piece right here. And OC is a radius. Well, we know this radius over here is 5, so OC must also have to be 5. OD. All of this is a radius. That's 5. That much of it is 2. That's going to leave this piece in here, OD, as 3. Now look at that right triangle. If you recognize your Pythagorean triples, this is one. It is a 3. Yes, that's 4. If you don't know your Pythagorean triples, shame on you. Or if you just prefer, you may use Pythagorean theorem. So you would do 3 squared plus, call this x squared equals 5 squared, and solve that, and you will get 4. If we move on down here to this one, given segment AB is 12, or the length of that chord is 12, all of that's 12. It's kind of hard to put in here. I'm going to put it right there in the middle. And the radius of circle O is 10. How far is the chord from the center? Now, when you're doing these types of problems, there's kind of a trick. And that trick is when you draw the radius in, draw the radius to the end point of the chord. So make that your radius. And that radius is 10. Then draw a perpendicular in from the center to the chord. I'm going to use the tick marks on my ruler to make sure I'm going perpendicular. So we've got this perpendicular going here. This is the piece that you want to find right here. That's what you want. All right, now a couple other things looking through here. We know that if we draw a perpendicular to a chord, it bisects the chord. That makes this piece right over here, this half of it, to be a 6. Half of 12 is 6. Now, you can try your Pythagorean triples and see if they work. Let's divide out the 6 and the 10 both by 2, gives us a 3 and a 5. 3, oh, that's a 3, 4, 5. And then double back by 2. Since we divided by 2 to get inside, we'll multiply back by 2, which means x is 8. So how far is the chord from the center? 8 units. But if you just said 8, that would be fine. If this bothers you, the triples, the numbers in the middle, go ahead and use Pythagorean theorem. Just do 6 squared plus x squared equals 10 squared. It's much faster if you know the triples, but you can always use Pythagorean theorem. Looking at number 3 down here, the chord shown is 15 units from the center of a circle with a radius of 17. As I said before, when you have these types of problems, draw the radius into the edge of the chord. So I'm going to draw a radius right here. Now if I label this diagram, the chord shown is 15 units from the center. So from the center, this distance, that's 15, in a circle with a radius of 17. And we want to find the length of the chord. Using our triples, this is an 8, 15, 17 right triangle. Again, if you don't remember that, please use Pythagorean theorem. X squared plus 15 squared equals 17 squared. Solve it, you will get 8. But we want the whole length of the chord. So the whole chord is going to be 8 doubled, or 16. If you know your triples, much faster than having to crank through Pythagorean theorem. Looking at number 4. Oh, this one didn't have any information drawn in the diagram. I just gave you the circle. The radius of circle O is 13 millimeters. The length of chord PQ is 10 millimeters. Find the distance from O to PQ. All right, well, let's draw this first. There's circle O. I don't want to draw the radius in just yet because I want to put my chord in here. Chord PQ is 10 millimeters, so I'm going to draw my chord. There's chord PQ. The radius is 13, so now I can put my radius in. I'm going to draw it to the end of that chord. So there's that radius, 13. That whole chord was 10. And I want to find the distance from O to PQ. So I'll put my perpendicular in here again. This is what I'm looking to find, that distance from the center to the chord. Okay, we know that this piece right here is going to bisect that chord. So half of 10 makes this 5. Oh, will you look at that? That's another triple. That's a 5, 12, 13. So how far is that point, O, from the chord? It's 12 millimeters. This one you need units on it. Since there were units given to you in the problem, you need units in your answer. Again, if you don't know your triples, please use Pythagorean theorem. Triples make things so much faster. They're hard to memorize at first, but once you know them, then it makes your life so much easier as we go on through this stuff. All right, let's look at this one. Two circles intersect and have a common chord 24 centimeters long. Okay, so two circles intersect, common chord, so that's right here. There's that common chord. It is 24 centimeters long. I don't want to put the 24 in there right now because it's just going to get too messy. The centers are 21 centimeters apart. So let's find the center here. You can estimate, that's fine. Estimate here. Again, that's kind of hard to put in there, so I'm just going to kind of draw it down here, that distance between those two is 21. I'm going to go ahead and connect those up. That light blue line, if you can see the color there, that one is 21 centimeters long. All right, now notice that we drew this piece in here. That's part of a radius. That means it has to be perpendicular to this chord right there. Which means then that that chord, which was 24, it got bisected. It got cut in half. So now I can put in that part's 12. And that part's 12 down here. All right, the radius of one circle is 13. Doesn't matter which circle you choose. I'm going to put it in the smaller one. That's 13. And we need to find the other radius. I'm actually going to put that other radius. I'm going to put it up here. That's what you want to find, is that other radius. Now this triangle right here is not a right triangle. It might look like it, but it's really not a right triangle. There are two right triangles in here that we are going to use. I'm going to use some color to kind of identify them. So here's this green one sitting right here. That right triangle. And then we're also going to look at this orange right triangle over here. All right, if we look in that green right triangle, just that one, got to see that 12 sitting there. We got a 12 and a 13. Oh, this blue part right down here, all of this, that's 5 then. That's a triple, a 5, 12, 13. If not, use Pythagorean theorem. And then, okay, now, I had to figure out this piece over here. Oh, the distance between the centers was 21. That much of it was 5. That means that much of it right there, 21 minus 5, 16. All right, it's getting kind of crowded in here, so I'm going to take this orange triangle over here, and I'm going to redraw it Sorry, I can't pick up my geometer. I'm going to redraw it off to the side. Here's my orange triangle. And we have a 12 here from there. We got a 16 on the bottom. We ultimately need to know what this is right here. So if we use our idea about that reduced triangle principle and divide both of these by 4, that makes this a 3, makes that a 4. Oh, we got a 3, 4, 5 going on. We divided by 4 to get inside, so multiply back by 4 makes that 20. That's the radius that you're looking for right here. So the other radius is 20 centimeters. If you don't know the triples, if you don't like this, then please use Pythagorean theorem. It's just a lot harder to go 12 squared plus 16 squared equals x squared, and then having to solve that equation. Much faster, again, if you use the triples. Hopefully you can see that, which is why I made you memorize them. All right, let's look at this next theorem down here. If two chords are equidistant from the center of a circle, then they are congruent. All right, so here's the picture. We've got these two chords right here, so chord AB and chord DC. We have circle O, and segment OX is perpendicular to segment AB. OX is perpendicular to segment AB. Segment OY is perpendicular to CD. OY is perpendicular to CD. OY to CD, so right here. And also segment OX is congruent to segment OY. OX is congruent to segment OY. Okay. We want to prove that segment AB is in fact the same length as segment CD. We're not going to do a formal proof. We're just going to show or kind of talk about that why they really are congruent. All right, to do that, let's go ahead and draw in segment OD and segment OA. Those are both radii of that circle. So we know then that segment AO is congruent to segment DO because they are both radii of the circle, circle O. That gives me this piece right here congruent to that piece. Okay, now remember in your Math 1, triangle AXO is congruent to triangle DYO by right angle hypotenuse leg. Remember RHL? Some of your teachers may just have called it HL. Which means that AX, segment AX is congruent to segment DY by CPCTC. Corresponding parts of congruent triangles are congruent. So that gives us this piece. AX is congruent to DY. Okay, now we also know that because these segments were perpendicular to the chord, that the chords were bisected, which means that the whole chords are congruent. Then segment AB is congruent to segment CD because the chords were bisected and the halves on each are congruent. Not a very formal proof at all. This is not something that I would expect you to do on a test or a quiz, but it is something that I expect that you can kind of follow along with. We're going to go ahead and look at a problem that uses this concept. Two problems, actually. So let's look over here. Well, another theorem. It's kind of the reverse of this. So this one says if the two chords are congruent, then they are equidistant from the center. So the last one said if two chords are equidistant from the center, then they're congruent. This one flips it around and says, okay, if they are congruent, then they are equidistant from the center. So if this chord and this chord are congruent, kind of hard to mark there, then they have to be equidistant from the center. So then XO is congruent to segment OY. And the last problem for notes today, segment AB is congruent to segment CD. All right, so AB, all of this, congruent to CD, all of this. OP, 12x minus 5. OQ, 4x plus 19. And we want to find OP. Well, right here, because these two chords are congruent, then we know these two distances are equal. So we can set up 12x minus 5 equals 4x plus 19. Subtract the 4x. 8x minus 5 is 19. Add the 5. 8x is 24. And x is 3. I almost wrote 23. X is 3. Problem did not ask us to find what x was, though. Problem asked us to find OP. So we're going to substitute right back in. OP is 12 times x, which is 3, minus 5. 36 minus 5 is 31. So OP is 31. All right? And your question for today that you need to upload onto Canvas is, what's the phrase that is on Mrs. Rachel's mug of tea this morning? And there it is. What's the phrase that is on Mrs. Rachel's mug of tea? Got it? All right, thank you very much. Please go ahead and do the section 7.2 homework. Have a good day.